So we have seen how a periodic function with period 2 pi can be written as a Fourier series in terms of sines and cosines, and we also looked at the Dirichlet conditions for convergence of such a function. So in this lecture we will show that there is an equivalent exponentials approach, right? So instead of sines and cosines, we could express a periodic function in terms of exponentials, right? So the two are completely equivalent, but in some contexts it's more convenient to work with this exponential form that we will lay down in this lecture, right? So you're given a periodic function with period 2 pi. So we are going to write this f of x as c naught plus c1 plus e to the ix plus c minus 1 e to the minus ix plus c2 e to the 2ix plus c minus 2 e to the minus 2ix, so on, right? So you have also these, now you allow for this index to take negative values as well, right? So in other words, we are writing this as a summation where n goes now takes all integer values from minus infinity to plus infinity, cn e to the inx, right? So to find these coefficients cn, right, so let's work this integral out, right? So you're doing this integral 1 over 2 pi integral minus pi to pi f of x times e to the minus inx dx. So now we have 1 over 2 pi integral minus pi to pi summation over m. Instead of n, I'm using m, it's a dummy index. Cm is e to the I mx. Then I have e to the minus nx dx. So I'm going to exchange sums and integrals, right? So which it turns out it's possible, right? So because we are working with functions which satisfy Dirichlet conditions, and this convergence theorems have been worked out. We are not proving any of them, right? So this is a legitimate thing to do because of the type of functions we are working with, right? So let's see this argument through, right? If you allow for this exchange of summation and integral, so then you have, right, so this integral is just going to give you a 2 pi times delta mn, right? If m equal to n, then you get a 2 pi. If m is not equal to n, right, this integral is going to be 0, right? So you can check this. And then, so what it does is basically it's going to pick out just one of these coefficients. So in fact, this integral is going to pick out for you the one coefficient that you're interested in. So in fact, this is a prescription for identifying any of the Fourier coefficients. So this is our rule. If you're given a function f of x and you want, which is periodic with period 2 pi, and you want to express this as a Fourier series involving these complex exponentials, then the coefficients are given by just this simple expression. So the advantage with this formulation is that it's just one single expression to remember. Cn, although you can argue for it and directly work it out, whether you're doing it with the sine cosine approach or with the Cn, if you have understood the logic of this. Cn is equal to 1 over 2 pi integral minus pi to plus pi f of x e to the minus inx dx, right? So this is nothing spectacularly new has happened here, right? It's just completely equivalent to the sine and cosine approach. We could have also just started with the sine cosine series, and in place of whenever you have sine, you replace it with e to the sine x can be written as e to the x minus e to the minus x divided by 2i, and cos x can be written as e to the x plus e to the minus x divided by 2, right? So if you do this in the sine cosine Fourier series, you will anyway get back the same result, right? So let's look at an example, right? The same example which you have already seen, but using this prescription. So let us expand in a Fourier series of complex exponentials this 2 pi periodic function f of x equal to 0 in the interval minus pi to 0 and 1 in the interval 0 to pi. So always we have to be careful with this c0 term, the coefficient corresponding to the DC part, so to speak, usually needs to be treated separately, right? You cannot blindly use this formula and think that you have the full answer, right? You always use some special caution to work out the DC coefficient. So C naught, although the formula is the same, right? But it's easy to slip in this evaluation of these coefficients if you don't make a distinction for C0. So C0 is 1 over 2 pi times just 1 in the interval 0 to pi, right? So the other interval doesn't matter, minus pi to 0, because you have 0 here for the function, and so you just get a half for C0. And for n greater than or equal to 1, so in fact also negative n as well, right? So I should say mod n greater than or equal to 1. So let me just say n not equal to 0. So for n n not equal to 0, Cn is given by this expression, which you can check is just 1 minus 1 to the whole power n divided by 2 pi ni. So thus we have this Fourier expansion. If you collect all these terms carefully, you can pull out a pi in the denominator, and there's an I in the denominator which you can shift it to the numerator, and you have a minus sign. The factor of 2 also is there, and then that is also, it cancels with one of the factors inside. And then so if you carefully look at all the factors involved, you can write down this Fourier expansion, right? So you can go back to the previous discussion about writing this in terms of sines and cosines, and convince yourself that indeed we had only sines, right? We had only sines, and if you look at the way I am grouping these terms, you are going to get only sines. So this expansion in terms of exponential is completely equivalent to the expansion in terms of cosines and sines, but in certain contexts it's more convenient to work with this formulation, and there are other contexts where that is more helpful, right? So so that's all for this lecture. We'll come back to exponential formulation for other kinds of problem later on, but this lecture is just to point out that there is an alternate, completely equivalent formulation for Fourier series. Thank you.